Okay, so in this video, we're going to look at how we might go about building an algorithm to predict mortgage eligibility and approval. And we're going to base this on historical lending practices. Again, this is a slightly different perspective to approaches that have been used when considering the HMDA dataset. Which was originally developed by Munnell, Tootell, Browne, McEneaney. Their main interest was to investigate the degree to which race influenced mortgage approval. And they applied logistic regression mainly to see if race was a statistically significant variable and what was the impact in terms of mortgage approval rates for minority applicants. Again, we don't explicitly consider that. We've done that before. In this video, we're mainly going to consider some of the machine learning techniques as proposed by Varian. We're going to deduct the question of discrimination here and focus mainly in terms of how do we develop algorithms to automate lending or mortgage approval, and then test the algorithms with actual out-of-sample data, and then apply a number of models, including logistic regression, support vector machines, k-nearest neighbors, decision trees, random forest classifiers, and then take the historical lending patterns and use that then to synthesize an algorithm that replicates those lending behaviors. So the lending algorithms created, therefore, not state-of-the-art. Okay, so in this instance, we're not looking to create the best approach or the most forward-looking approach. We're just developing algorithms on the basis of historical norms, flawed or not, and then we can use these as benchmarks to appreciate future patterns in terms of lending, and then maybe how lending changes over time. Okay, so to get our data, you can download the data using this link here, and this will bring you to a CSV file. Now, I've already got this on my machine, but you can just download here. So if you hit this button, it'll download into your downloads. I have that data available already on my machine, so to upload it into this project, I come over here to the folder icon, and then I go look for content, the content folder, because this is where we can import our data and then upload. And then in my case, the data here is in my desktop, and I'm looking for a HMDA, and it's a CSV, right? So it's CSV, so we'll just upload it. Now there can be a little bit of latency here, may not instantly. That time it loaded very quickly. May not happen like that. You may have to wait a full minute, maybe 2 minutes, to see your data appear here. But once it's there, we can read it in once we import in the pandas library. Okay, so let's just import in the matplotlib for graphing, seaborn for graphing, and pandas then for data manipulation, and then reading our CSV file. The name of the file, HMDA, is, we can read in. So read the data. We're going to call it HMDA, although the name, it was HDMA, which I took from an ECDAT package. Okay, so HMDA, and then we just do some basic descriptive statistics, and it's giving us just 7 descriptive statistics. So we might want to see more than just that, but basically it's taken the numerical variables and it's given us the mean, the standard deviation, the minimum, the maximum. Okay, so that gives us some sense of what's there. In the data set, we have DIR, HIR, LVR, so the debt to income ratio, the household expense to income, loan to value. You have the credit scores, the mortgage credit scores, the unemployment of the applicant. So each row in our data set is made up of applicants, and we have here data relating to the unemployment rate in a given applicant's profession, and then condominium, which is misspelled, but it's I suppose an apartment, right? Okay, so we have some descriptive statistics, but this is not the entire data set. We need a little bit more here, and the data description, which comes from the original HMDA data set, DIR is debt to payments. So this is, if you like, creditworthiness values. We have HIR, household expenses to income ratio, loan to value, so the size of the loan compared to the value of the property, consumer credit score, MCS is mortgage credit score, pbcr, public bad credit score, DMI, denied mortgage insurance. So if you didn't have mortgage insurance or weren't eligible, or refused denied mortgage insurance that was recorded, whether you were self-employed or not, whether you were single or a couple, the unemployment rate in the applicant's profession, whether you're buying a property, was it a housing, was it a standalone, was it a dwelling, or was it an apartment, the race of the applicant, and black here denotes African American and Latino, and then deny, which was whether you were approved for mortgage or not. Now it's worth noting, I've done some analysis of this, and that's available in Vinegar Hill data labs, and the basic tidyverse, or I've done some of the preliminary analysis just looking at the descriptive statistics here. So that's now the analysis looks more in terms of the role of racial discrimination, and then trying to control a little bit for the creditworthiness, but there is a breakdown, fairly detailed breakdown and description of each variable. So that might be something that could be referred to. Okay, so we're looking at our data. We want to create a series of algorithms. Let's have a look. We'll do some initial Panda exploratory data analysis here. Not much. More of that is provided on Vinegar Hill. We'll go into the table of contents just so that our stubs appear here. If we run the HMDA data set and call up head, we get the first 10 rows. Now, what we observe is kind of the typical values there. An interesting one is the final 5 rows, right? So we might just do tailed here and take note of something. In the final rows, which each row represents a given applicant, there was 2 cells that weren't populated. So the public bad credit record, there was no entry here in the final, and also self-employed, there was no entry here. Also the credit score was 2.11. All the other values go from 1 to 6. And likewise here for the mortgage credit score, we have 1.72. So this final row here seems to be is populated with sometimes where there's no entry, where we've missing values, and then the values look corrupted in 2 of the cells. So we might exclude, and we can inspect the data in this format and run through the different data types and so on. We could get a measure of, we have 2,381 applicants. We have 13 columns of data. if we wanted to take a look at, without having made any changes, the data types, right? We have basically floats and objects. These are, the objects seem to be the variables that are have classification. So if we look at the pbcr, DMI, what we're observing is they're no and yes. So in theory, these are categories, right? No and yes. They're not just words, right? The words have meaning. So we will have to change these variables later on from just being objects into categories, right? When we run a check here to look at our data, we notice that the PBCR, we're missing 1. And when we sum up all the missing values in self, we're missing 1 cell. Again, point out where that is. That's the very last mortgage application, mortgage applicants. So it's these two here where we have the missing values, and already I've mentioned these look corrupted as well. The credit score, the mortgage credit score looks corrupted. So we need to correct for that. Again, we've checked for the missing values. Now, one way we could just eliminate the applicants with the missing cells, just 1, so there's not that many. We could create a new data frame and drop from our rows any cells that are missing. So the rows that have cells that are missing, we can drop, and that then, if we run again to see what missing values we have now, you can see we've purged those, and we can take a look at the shape now. We've only removed 1 row, so we're still left with 2,380. Originally, it's worth noting we had 2,381. So we basically eliminated the last row. We can get some more information then in terms of our values. We have floats and objects. We can have a look at the unique values for those variables that seem to be classification. We have public bad credit record. You either have it, yes or no. Were you denied mortgage insurance, yes or no? Are you self-employed, yes or no? So it's just 2 categories, 2 values. There was 10 different professions considered. If you're buying a condominium or not, that's a binary variable. Are you black or not? That's a binary variable. Are you denied your mortgage or not? In other words, if you were not denied mortgage, your mortgage approved. Most people, their mortgage were approved, but there's only 2 outcomes. So there's many of our columns here that have binary variables and really are categories, and we need to set that up. Okay, now we might look at some of the just do some basic data manipulation to look at the loan to value, and we can do that in terms of sort our variables in terms of the lowest loan to value to the highest. We can then perhaps when we look here at the condominium, this is something that Varian does. We might change, there's a misspelling there. So we can change that by saying, look, the DF columns, this new data frame that we're using, the 2,380, we can change the condominium to say condo. And then when we run and go in descending by saying ascending is equal to false, we have descending, and we take the top 10. You can see condominium has changed to condo by applying this term in our DF columns. And then we go from the highest LVR, and that's extremely high. LVR of 1.95 would mean that the loan is almost 2 times the value of the property. Banks typically don't like to do that. And then we go down. We can look at the tail also, and that would bring us to the LVR, the lowest LVRs, right? And LVR going down to 0.02. So that's a tiny amount of lending or borrowing in relation to the value of the property seems a bit unusual. Okay, we can have a look then at the breakdown of the black variable. There's 2,041 applicants who are not black or Latino. There's 339 who are. There is 2,103 who are not self-employed. There's 277 applicants who are self-employed. There's 1,444 who are not single. There's 936 who are single. There was 1,694 who are not buying a condo, and there's 686 who are buying a condo. The 2,095 were approved. So not denied means approved. So 2,000, the bulk of people are approved their mortgage application, but there is a group of 285 who are denied mortgage. And then out of the 2,380, there's 2,332 who were not denied mortgage insurance. That means they were eligible or accepted for mortgage or approved for mortgage insurance. Only 48 were missing out on mortgage insurance, who were denied mortgage insurance. Okay, now we can take some quick summary statistics here. And we can look at, just group our data by categories and do some counts. Now we can just change the order of this. And in the first category, put in those individuals who are not blacks and not African American or Latino. And that's the majority of the population. So that's 1,852 who are approved for mortgage and 189 who are denied mortgage. And then in the African American or Latino grouping, in this pivot tabling, we have 243 who were approved for mortgage, but 96 who were denied. Now we can take a quick look at, and we won't focus on this too much, but if we want to get a sense of how important then this race ethnic grouping is, or ethnic affiliation or grouping, if we take the 189, take 189 and divide that by the 189 plus the 1,852, that will give us, for the total population, the level of denial in terms of being approved for mortgage. So 9% of the majority, so non-Black, non-Latino, non-African American population, 9% were rejected for mortgage. For the rest, for the African American and Latino populations, those numbers are, the rejection rate seems to be higher. Now, in the original paper by Munnell et al., this was the central trust. We're not going to examine this so much here. We're just going to note in a very basic way, the statistics. So the rejection rate, mortgage applicant rejection rate is 28% for these minority populations, while for the rest of the population, non-minority population, was just 9%. So there's quite a big disparity. And that was the central trust and the focus of Munnell et al. 1996, and then Varian applied machine learning techniques to investigate this a bit further. We're not going to look at that so much. We'll just take note. Our key interest here is to set up algorithms to automate lending decisions, and based on this historical data set, even if the lending decisions were flawed or not. Okay, so we do some seaborne visualizations here, and we do a count plot, and we can look at those. So we see that the vast majority of people are approved for mortgages, and just a small slither are denied mortgages. When we run some visualizations here to compare the breakdown between the different ethnic groups, we can see proportionately if you're African American, you're going to be denied mortgage much more often. If the rest of the population seem to do have much higher approval rates for mortgages. Interestingly, if we look at the LVR, the loan to value ratio, which is a key measure of risk, we can see here that those typically, those who are rejected for mortgages have higher LVR. Those who are accepted for mortgages have lower, but there's quite a wide spread. Counterintuitively, perhaps, when we look at black applicants, many black applicants, so we run here, if you are African American, Latino, it's this browny orange color, otherwise blue for the rest of the population. But African Americans, Latinos are accepted for mortgage with higher LVR. So the median LVR for African American Latino is a bit higher. Now that might suggest that there isn't a racial element explicitly, that when we control for credit risk, the banks actually are accepting higher credit risk here from those populations and still lending. Another issue that maybe needs to be addressed here, maybe these higher LVRs signify much higher rates of interest and punitive rates of interest are applied. It may also be possible that Munnell et al. Didn't have, in terms of establishing whether there was a racial element or a race feature heavily in terms of lending decisions, their determination of racial discrimination was linked to the amount of loan approval or the differentials in loan approval between the different groupings, ethnic groupings. That may not be a definitive measure of discrimination. One of the concerns here that has emerged in recent years since the financial crisis, the credit crisis, the securitization crisis in the US, and the subprime meltdown, was that many African Americans did receive loans, but often these loans were predatory. So just being approved for loans, it doesn't necessarily mean that there isn't other types of racial discrimination going on. If a loan is predatory, it is a loan where individuals have little hope, perhaps, of paying it back, but still the mortgage broker will do a hard sell, misappropriately sell a mortgage product that leads the mortgagor into difficulty and maybe having to sell out the property to cover the mortgage repayment. Again, that was partially the story since the early 2000s. A lot of predatory lending targeted at marginal groups, targeted at Latinos, targeted at African Americans, and the volume of lending that is and the volume of mortgage approvals may not necessarily translate into more less racially segregated type society, predatory lending, where punitive rates of interest are charged on applicants, mortgagors. That might actually signify a greater degree of dysfunction and toxicity in financial intermediation. Okay, so that's another day's work. We're not going to touch that so much here. Just to mention it, now just to eyeball a little bit of our data, we could look at, first of all, consider whether individuals are denied or not. So if you're denied, you were refused your mortgage. If you were not denied, you were approved. And maybe there is a little bit more, those individuals that had high, that were denied were more likely to be in this quadrant with the higher LVR, the higher DIR. That would appear to be true, although we have some confounding single instances here, but there is more of a clustering. So we don't get to create a straight line here easily. Perhaps if we just put in DMI, which is denied mortgage insurance, and ran this graph again, you could see those who were denied mortgage insurance, they clearly, you could draw a line here perhaps, and we find very few instances below, you know, here where individuals are, if you have a very low LVR, a very low HIR, LVR and HIR, you tend to get mortgage insurance, right? And it's, but again, it's not a completely clean type of set of lines. And so perhaps what we're looking at here is a lot of human behavior. Each applicant is being assessed perhaps by different banking institutions, different lending officers. So it's hard to really aggregate all this into very clean delineated patterns. So we do have that. That's an issue that arises with this data. We could do some a correlation, write out a correlation report, look at the size. Now we had 13 variables, but we're only getting 7. And that's, we have to make a change to our data. The problem is we have to change these objects into other types of variables. So we're going to encode them as categorical variables, right? And when we come out and run our recheck the data types, we've now converted those to INT64. Okay, now if we rerun, if I go back and rerun after making those changes, you can see now we've 13 by 13, and we can run the correlation matrix, and we get the full 13 variables. And we can just look at deny mortgage just to see what's highly correlated. If you're denied mortgage insurance, there's a high correlation, or reasonably high. If you have a public bad credit record, at first glance, that seems to be quite significant. It's 0.3. The other variable here is the credit score. Loan to value is 0.2. Then the variables that have seemed to no effect, the unemployment rate in a given applicant's profession, whether you're buying a condominium or not, is not that important. HIR is not seen as being that important, but then that's highly linked to the DIR. These two variables tend to be linked together because there's income in both. But credit score, here's public bad credit record and denied mortgage insurance. These are variables that seem to be the strongest. Okay, so that's just some preliminary analysis, and maybe we find that in our analysis. Now we've already changed the designation to categorical variables, and we can see when we output the data types, the categorical variables, the PCBI, the pbcr, DMI, and so on, they now are categorical. Now, next step involves us separating our data into the independent variables, or the features, and then the value we want to the independent variable, the target variable, the variable we want to predict. So we want to create an algorithm, and we want to use a classification, create a classification type algorithm that we can predict this binary. Were you approved for your mortgage or not? And then we want to split up our data so that we take the 2,380 observations, and then 20% of our data we'll set aside. 80% we'll use for training an algorithm. So basically, with the models we have below, the logistic regression algorithm, the K-neighbors classifier, the support vector machines 1 and 2, Gaussian naive, Bayes classifier, a decision tree classifier, and a random forest classifier, we will run these models from sklearn libraries that are available. So from sklearn models, we'll import the train test split, and we will import in then logistic regression and so on, these other models from sklearn. Okay, so we've split our data into the 20% testing data, 80% training. Then we define the models. We've imported the models, we define them. We're going to estimate using the train predicted the Y train using the X train, and we can see how they were split here. And then we test those model in sample. So we estimate the accuracy of the models, the training models, and of course we're getting bumper, really good accuracy, random forest, excellent, decision tree, excellent, and so on. So they're all, for the training data, the models are performing extremely well, if you like, in sample on the training data. I suppose the real test is reporting the accuracy of the model with the testing data. So we want to take that 20% of data we reserved and now apply these models and predict the models using the testing data and see how well these in the testing data, how well the models do. And then we create a series of confusion matrices, right, based on each of the models. So we have model 0 to 6, logistic regression, K nearest neighbor training, support vector machine, just two of those, Gaussian naive Bayes training, decision tree, classifier, random forest classifiers, model 6. And for each of those models, taking the testing data and applying each of the algorithms we've created, we then get these confusion matrices, and you can see the level of accuracy has dropped on our model. Now, to understand how well the accuracy here, we're taking the true positive and the true negative, and then we're dividing the true positive, the sum of the true positive and the true negative, we're dividing that by all the other variables, all the other values here in the confusion matrix. These ones off diagonal are mislabeled. So this is the error. The 6 and the 38 represents the error, the 411 and 21. Now remember, it's 2,380 applicants. The training is 80% of the data, then 20% of the 2,380 then is the sum of these. So if you like, if we take the sum of all of the 4, then we get the number of cells. We can take a look at that for a moment. Just if we, for instance, take the 407, and then add 10 and add 41 and add 18 and run that, you can see we get 476 in the 476 rows in the testing data. Now, if I go to the confusion matrix above, I should get that 476. So if I take the 374 plus the 43 plus the 35 plus the 24 and run that, I should also get 476, which I do, and so on along the way. To understand a little bit what the confusion matrix here is spelling out, we could use this graph here. So maybe I'll just put that to one side here, bring down the confusion matrix, and then just bring across a little bit so that we can understand what the confusion matrix. So we have 476 applicants who are set aside and put into the testing data. We're looking at the model performance. So we've taken each of the models, the logistic regression, the K nearest neighbor, and so on, random forest, all of those 7 models. We have 7 models in total here. And we've looked at the training accuracy, which is all very high. That's a little bit flattering. So we would like to test against the testing data, the sort of outer sample data. And we've used confusion matrices here, where the true, if you like, we have from our predictions, a few things are going on. We have true positives, we have true negatives. So true positives, true negatives. We've false positives and we have false negative. Okay, so true positives, that is, we out of the 476 in the testing data set, 21 were predicted to be denied mortgage and were actually denied. And then we had true negatives, 411 who were predicted to be approved mortgage and were actually approved. So both the prediction and the actual coincide. The prediction about being denied and the actual coincide. But then we have the false positive, the 6 here denotes the false positive, predicted to be denied mortgage but actually approved. And then the 38, false negative, predicted to be approved mortgage but actually denied. Okay, so you can link the discussion here in terms of the confusion matrix over to the graph or the tabulation that we have here. If we take the second one here, which is the K nearest neighbor, it doesn't predict as many mortgages denied, right? And there seems to be more error, slightly more error both here in the true false positive and in the false negative. So we're getting a lower accuracy. And remember, the accuracy is being measured by taking the true positives and the true negatives and dividing by the sum of all four, which you recall the sum of all four is the 476, the total number of rows in the testing data set. So we're taking, to get the accuracy, we're taking the diagonal, the 411 and the 21, and we're dividing by 476, right? So if you like, just to see that for a moment, we can come down below here and we can say, look, take the 411 and the 21, 411 plus 411 plus 21, that's equal to 432. And then we divide that 432, we divide it by the number in the rows in the testing data set. So 476, and we get 9075, and that's what we have here. 9075.6 is the level of accuracy. So we're taking the diagonals, the true positives, the true negatives, and then dividing by the total number. And again, for the accuracy, we're taking the true positive, the true negative, and dividing by the sum of all four. Turns out that the logistic regression here is performing quite good, very well. It's probably the best in terms of all the models that we have here with our testing data set. The random forest is also reasonably good. And then models 0, 1, 2, and 3 are also quite good as well. So 2 and 3, the support vector machines in this instance, seem to perform incredibly enough. Okay, let's remove that. We've explained a little bit then the confusion matrix. Now, again, this bit, the next section then, really what we want to investigate here is how do we use our models here to predict. And so, for instance, if we took model 6, copy selection, and I go into model 6 here, control V, and let's say I want to take model 6, so that's the random forest model, and predict with the random forest model. Remember, model 6 is the random forest model, and I want to predict for the 476 applicants in the testing data, what are the outputs? And you can see the random forest is predicting that applicant 0, 1, 2, 3, 4, 5, no 6, 1, 2, 3, 4, 5, 6 is denied mortgage, 7, 8, 9, 10, 11, 12, and applicant 12 is denied mortgage. But if I then do that with logistic regression, model 0, and predict, what we observe is the logistic regression is not as good at picking out. It's a little bit more conservative picking out in terms of the mortgage approval. Let's go back to model 6, run that report again. Now we could compare against, we could look at, let's say, the first 6 and see from the actual data using the testing data, was 6 actually denied mortgage? So if we take X, the head, the top 6 rows, we can look at the predictive variables, the future variables, and then compare against the actual, right? So take Y test head, and we can see 1, 2, 3, 4, 5, 6. So the 6th row, it's actually true, the applicant was denied mortgage. And then if we took if we were to look at the, let's say, the first 12 applicants. Okay, so let's go model 6, 0, 1, 2, 3, 4. That's 6, 7, 8, 9, 10, 11, 12. So if we take the first 12 applicants in the testing data set, we can see here, well, for 1, 2, 3, 4, 5, 6, the credit score was 6, which is the worst credit score. And that's the random forest model, when it takes this and predicts should the individual be denied mortgage or not, the random forest model is predicting should be denied. And then when we look at the 12th applicant here, they have relatively high DIR, but the loan to value ratio is also very high. The average LVR was about 70%. This LVR is really high. When we test the applicant here, we come to 12, the random forest model is predicting that individual would be denied, right? That individual would be denied. We could take the 12th observation here, 12, and run and see, was that actually true? And when we go down to the 12th applicant in the testing data set, we can see they were actually denied. So in both instances here, the random forest model is doing quite well in running in testing here. We could do, again, I think I have it below here. Yeah, if we run model 6, so that's the random forest model, and predict using the random forest model, take the first 12 applicants in the testing data set and run that report, you can see we get applicant 6 and applicant 12 are denied mortgages. So weren't approved for mortgages. So the random forest model is doing quite well. And we can then test to see, well, take the actual top 12 applicants in the Y test. The Y test is the variable we're trying to predict whether you're approved for mortgage or not. And you can see the 6th, if we take this, the 6th applicant here, they were denied mortgage insurance. And if I take the 12th applicant, sorry, they were denied mortgage, and the 12th one was denied mortgage also, right? And we can look at their statistics in terms of the predictor variables in the testing data set. In the X variables, or the attributes, we can see that applicant 6, so 1, 2, 3, 4, 5, 6, they had a very high consumer credit score. That means that's the worst rating, number 6. The ratings go from 1 to 6. 6 is the worst. And then the loan to value ratio of applicant 12 was over 100%. That's a bit risky. The average was about 72, 75%. So this is way over. Random forest is picking up on these and predicting that both applicants running our model with just the top 12, right? It's the random forest model is predicting both of those applicants are not going to receive the mortgage. Now, if we run the entire test data, this is the entire output. But if we just run the first 12, if we just report out the first 12, then applicant 6 and applicant 12, this is what the algorithm is predicting. The random forest predicting, look, no, not going to get mortgages for these two here. Now, with the logistic regression model, model 0, we do the same. It's not as good as picking up those. So even though logistic regression is more accurate, it's not as good as picking out applicants who fail in getting mortgage approval. We can look at model 1, see how well it does. It doesn't pick those up. What about model 2? It doesn't pick up. What about model 3? Run this, and remember each of the models here is logistic 0 to 6 are these 6 models we're going to use here. And if we use, so we're on model 3, what about model 4? Okay, model 4 picks up applicant 6 as being predicts denied and actually was denied. What about applicant 12 who was actually denied? Model 4 is not picking that up. What about model 5, which I think is the tree classifier, not the random forest, the tree classifier? It doesn't pick up, it inappropriately picks up applicant, the second applicant, and it misses the 6th applicant and the 12th applicant, and then a random forest here, and just taking the first 12 is getting it correct. Okay, so random forest seems to be quite good in terms of picking those, but then overall, when we look, logistic regression had more true positives, right? And the model with the highest number of true positives was model 4, and model 4 was a Gaussian naive based model. So it's better at picking true positives, right? True positives mean predicted to be denied mortgage and actually were denied mortgage. So that's an algorithm then that we've created. Each of the models then denotes is an algorithm, and we can pull out our predictions in terms of whether the applicant, whether the algorithm would determine if the individual should get a mortgage or not. And this is one way, one approach we could have to automating mortgage decisions, the mortgage approval process, and it allows us to extend the analysis in terms of training the algorithms to automate lending or mortgage approval. And then we can test the accuracy of this, whether this is a good model, whether it's a flawed. That's not in terms of the original expertise of the individual loan officers. We don't have that here. What we have is we're taking each of those lending decisions, training an algorithm based on the training data set, and then we have basically an algorithm that can predict based on the information, the mortgage applicant's information, whether they should be approved for mortgage or not, coming back as a 0 or 1.